Hello, everybody. My name is Michael Miller, and I'm here to talk about a data structure for a system that I'm building. It's called neural propositions. For this talk, we'll cover the inspiration for the data structure, which is Jean Piaget's book, The Development of Thought. It's from, and then we'll talk a little bit about assimilation and accommodation, which everybody pretty much knows, but we'll talk about it from a computational perspective. And then we'll talk about affirmations and negations, which was a problem that Piaget discussed in his book, and one approach to solving it. And then we'll talk about neural propositions and inference with neural propositions. And then finally, we'll wrap up with a discussion of the PAM P2 system, and then the larger system, mind servers. So the development of thought. So Jean Piaget wrote this book, The Development of Thought, in 1975. First translation came out in 77, and then second translation in 85. And essentially he covered the process of equilibration and the construction of structures. So equilibration, from my interpretation of this reading, is maintaining stability in a system. It's a combination of equilibrium plus calibration. Maintaining stability. So equilibration is about how to maintain stability in a system when disturbances inevitably occur. Namely, what mechanisms maintain stability, which structures are modified, and how to modify the structures. Ironically, though, he didn't go into detail about what specific structures these are. And so this talk is a proposal at a computational structure that can be used. Jean Piaget said that cognitive equilibriums are close to equilibrium states mentioned by Prigogine. They resemble biological equilibriums, which are homeostatic, and dynamic equilibriums, which are homeoretic or trajectory-oriented. When we talk about maintaining stability in equilibrium, we have equilibrium where the system is close to reality. We have equilibriums where the system is very far from reality. And then we can talk about also disequilibriums. So there are kind of two kinds of disequilibrium, which George Soros pointed out in his financial writings. Dynamic disequilibrium, where reality stays constant, but the system initially starts out close to reality and starts to diverge until it hits an inflection point where it diverges wildly. And then eventually, the divergence forms a crash, which brings the system back into alignment with reality. And then we talked about static disequilibrium, where the system maintains its perspective on the world, or viewpoint on the world, however reality is changing underneath. The central idea of the book, Development of Thought, is that knowledge proceeds not from the experience of objects, nor from any innate programming performed in the subject, but from successive constructions, the result of constant development of new structures. So we'll have some terminology. An element, for our purposes here, is just a system or environmental entity, something internal or external. A scheme is just a simple proposition about elements. Assimilation means creating a new scheme. It means just adding elements to a scheme. And accommodation means mutating a closed cone scheme. It means copying a scheme and tweaking it or changing it in some way. So let's take, for example, some elements. We have a system, we have the environment, we have an interior elements B2 and C, and we have an external environmental element B double prime. So to assimilate it means just to form a scheme and pick up all of the elements, both internal and external. So assimilation means just to create a scheme. Accommodation means to just copy the scheme and change it slightly. So we have our original scheme was B2 and B double prime enable C. Our accommodated scheme is B2 and B double prime enables D, so where we modified C. And then we can accommodate the scheme again in a different way, where we say B2 and B single prime enables C. So simply accommodation means just to copy something and modify it, and assimilation means just to create. So now we can talk about interaction cycles, which are, the core of this theory. And we'll just talk about it at a high level here. But an interaction cycle of interaction, is a functional dependency established among external or internal schemes, subsystem, or the entire system. And he referred to it, his language is a little bit confusing, but he referred to an interaction, what I call an interaction cycle, as schemes of assimilation. So he reused the word schemes, but it's a little bit confusing. And you have to read multiple interpretations to actually kind of get the gist of what he's talking about. So he says interaction cycles, like organisms, cognitive systems are actually both open in the sense that they undergo exchanges with the environment and closed insofar as they undergo cycles. So if we call A, B, and C parts forming a cycle, A prime, B prime, and C prime, the elements of the environment is required to feed the system. So we can depict this graphically. Oops. So there are a couple of different kinds of interaction cycles. We have physical, logical. We have the first level is random. The second level, type 2 interactions are deliberate, and the third kind are experimental. So different kind of interactions. So as we were saying before, if we have A, B, and C, the parts forming a cycle, A prime, B prime, C prime, the elements of the environment required to feed the cycle. So if we depict that, here we have A, B, and C, which are elements in the system, internal, all the way to Z. And we have A prime, B prime, all the way to Z prime. So we assimilate these elements. So now we can say that A and A prime enables B and B prime enables C, all the way to Z and Z prime enable A. So now we've assimilated these elements, and we have a stable cycle. So this cycle can represent anything. It can represent maybe an animal foraging in the wilderness or existing. It can represent a person in the workforce, work environment. It can represent anything. We have all these different kinds of interactions, any kind of interaction that goes on. So what happens is that we have a perturbation or disturbance, and we have a new element. Maybe our existing element goes away, and the new element is introduced. And as a result, our cycle is disturbed. So we have a disequilibrium. We don't have the elements, we can't continue our cycle because we no longer have this B prime, B double prime. So for example, in the case of an organism, maybe we have a little cat in an alley or something like that, and it's used to chasing mice and eating mice to survive, and all of a sudden, there are no more mice. Maybe their snakes came around and ate all the mice. However, there are birds in the environment. So what is it going to do? Is it going to starve, or is it going to adapt to the fact that there are, it has to, adapt to the fact that there are no more mice. So if the system rejects B double prime, so for example, it says, well, I don't want to eat birds, then we have the end of this cycle, and the end of the organism in the biological sense. And, in the cognitive sense, maybe B double prime represents new technology. We have a worker in the workforce who is used to using old technology and fails to adapt. So maybe the end of that particular person's career or something. But it's any kind of interaction. If the system accommodates B prime, so it adapts itself or adjusts itself. So to accommodate, again, we copy and include, or copy and modify. So the cycle is stabilized. So now we have differentiation, and we have an improved cycle, because now we have the old available to us if it represents itself, but we also have a new structure. So we have a new equilibrium. This is the essence, I think, of what he was talking about. But we get into a problem of affirmations and negations, because when we were talking about element B here, and this particular scheme relied on B prime, but now we have to adjust this element B in order to take in the new element. So we have to stop eating mice and now start eating birds or something like that. B becomes B1 plus B2. Piaget said that B is mutated into B2 in order to accommodate B double prime. However, the original B, now called B1, is also retained. We don't change something and get rid of it. We change and we keep the original and we add something new. So therefore, B1 is the original B, but without B2. And B2 is the B, but without B1, or B2, B and non-B1. So we need to make these negations explicit. Right now they're implicit. So typically in a Euler or Venn diagram, we represent the universe as either a square or a circle. I made it a circle. And when we talk about a set A in the universe, we describe what is non-A as outside the universe. And when we talk about a set A being comprised of A1 and A2, the negations are implicit. So when we talk about A equals A1 plus A2, we can also say A1 equals A and non-A2. So A1 here equals all of A and non-A2. We could talk about A2 being A and non-A1. But here, negation is implicit. What we're really saying is A is A1 and non-A1, and A2 and non-A2. But what we want to ask is, what if non was an entity rather than a function? Typically, non-A1 and non-A2 are functions or operations on A1 and A2. But what if we explicitly made non-A1 and non-A2 entities instead of function? So that we do this so that negations can also become candidates for assimilation in the computational system. Jean Piaget said that typically it's easy for us to figure out the positive characteristics of things, but the negative aspects are laboriously constructed. So we want to make things simple for ourselves in a computational setting, which is easy for us to do. So here we defined A as A1 and non-A1 and A2 and non-A2, with negations being made explicit. So we have A1 and non-A1, A2 and non-A2. So for us, it's easy to do that. A1 is no longer A and non-A2, it's more than that, and the same for A2. So here we're trying to move negation from a function to an entity. That way we can better select them for accommodation purposes. So we can talk about A and non-A. We can talk about B and non-C. We can talk about B and non-B. We can talk about C and non-C in our universe. So now we have a way to describe our world. And let's call the thesis the positive characteristic, the affirmation. It's called the antithesis, the negative characteristic. And a monad is either a single thesis or antithesis, and a dyad is a thesis-antithesis pair. So we say a dyad is the thesis, A, and the antithesis, non-A. It's the pair of them together. Whereas the monad is either one or the other. So now we get to neural propositions. So in neural propositions, we have monads, which just represent any entity, either external or internal. And they can be active, neutral, or inactive. We have dyads as well, which represent the thesis and the antithesis. And actually, we have a shorthand for it. We just make the circle half like that. We also have schemes, which incorporate these monads. And in a scheme, we have a portion which is a name or an identifier. We have the relation that it represents, and there's a set of relations. And then the arguments for that relation. They can be unary, binary, ternary, or n-ary. So we have a scheme, for example, P of xy. We can represent it either as the relation P of xy or just simply Pxy. And we have reification. So reification is making an entity. And it's taking an entity and giving it a name. We have monemes, which are schemes which are reified by monads, and dynemes, which are schemes reified by dyads. So here we see the scheme and the monad, the thesis that reifies it. So this represents all of this. And we have a dyneme, we have the positive and the negative, which represents this. So now we can get to neural propositions. So a neural proposition consists of a reifier, a scheme, and arguments or terms. And this particular one represents R of the set M1, M2, and 3. And coincidentally, it kind of looks like a neuron as well, because a neuron has dendrites, it has a body, and it has an axon. And we can use this coincidence to actually flow activation through it. So we have a proposition, and we can flow activation through the proposition. Let's talk about differentiation and integration. So Jean Piaget loves the term differentiation. And I had an aha moment where differentiation is just mutation. It's simply changing something. That's all it is. It's the same as our process of accommodation. We copy and we modify. Integration is recombination, simply crossover. So we can integrate and differentiate things. So example of differentiation, we have a scheme A1. And to differentiate it, first we copy it, because as he said, we don't do anything destructive. We always do things constructively. So we copy it, and then we modify it. So we're going to modify argument Z. So now we've differentiated, we've mutated it. And then we have integration. So if you wanted to integrate these two, we copy them, and then cross over or recombine them together. So now we have addressed differentiation and integration. It's basically mutation and or accommodation and recombination. And then there's the special case that Piaget talks about in the development of thought, where A becomes A1 and A2. So we start with the scheme A. We need to preserve this, but we also need to mutate it. So we take the original scheme and we create an option between the original and the new. So we insinuate another scheme which gives us the original and the new. So now we have neural propositions. We can mutate them, differentiate them, integrate them. We also have dimensions upon which we can activate them as well. So we have both a fact dimension and a goal dimension. So we have multiple dimensions for activation. We can flow activation upwards from maybe our percepts up to higher level concepts. And actually, we can flow activation laterally. If for each relationship that we define, because since it's a computational relation, we can define whether or not the arguments flow into or out of the system. So we can define efferent or afferent terms for each relation. We can laterally flow activation from afferent to efferent terms and upwards from terms to reifiers. We can do the opposite as well, flow activation down. And then we can, for each particular type of relationship we want to define, we can define different kinds of ways to merge activation. So we can merge we can have pass-through activation, negated activation, we can AND things together, we can NAND them, we can OR them. So now we get to inference. So now we have a structure, and we can infer things from our structure as well. So a simple taxonomy, for example, in normal taxonomy using frame systems, things are hierarchical. Here, things are horizontal. We're talking about items on a particular plane or tier. So we can say Albert Einstein is an instance or a case of a physicist. We can say Jean Piaget is a case of a biologist and psychologist, or an instance of a biologist and psychologist. We can say physicists, biologists, and psychologists are types of scientists. We can say scientists are types of academics. We can perform analogy. We say the water in the soil in the Philippines is high, the rainfall in the Philippines is heavy, and also that the rainfall in Thailand is heavy. So because of these things, we can infer analogically that the water in the soil in Thailand is also high. We would have a specific process that looks for analogical relationships. We can do deduction. We can say that the climate, a climate of a country, tropical, implies that the temperature of the country is warm. We can say Thailand is an instance of a country. And we can say the climate of Thailand is tropical. Therefore, that would imply that the temperature of Thailand is also warm. Then we can do perception. We can have a device which sends a data set, sensory data set, to a component. The component can take that data set, analyze it, and assert propositions to our system. And then each proposition is a percept relationship. You know, percept can be a feature of the data set, or it can be just a raw element of the data set. And then our system would highlight or activate different features. And actually, this brings up a good point. Activation in this proposed framework is temporal. It's not binary, on or off. We just timestamp something as being activated. And by timestamping it, we get automatic decay. And we define in the system a window of activation so that things that are within the window, maybe the window is 1 minute or 10 seconds or a couple milliseconds, whatever our activation window is, and will be defined on a tier basis. But things that are within the window are active, and things that are outside of the window are inactive. So we have our percepts here with our data sets. So the first thing we can do is we can say that things occur in unison, and then we can say that things occur in series. And then we can continue to form unison and series relationships. And then we can also form alternation relationships. We can see that this leads to one and it leads to another, so we can define options as well. So that's perception. We can handle induction. Once we have our layer of unisons, options, alternatives, and series, we can induce entities. And then we can induce instance relationships and also type relationships. So we can start to build an ontology from our sensory data sets. We can predict things as well. We can say that we've observed that this particular stimulus leads to this particular result. And we can form an expectation that this stimulus will lead to this result within this time frame. And then, once we've experienced it, if we see the stimulus again, we can predict at a particular time, between this particular interval, that this expectation will be reactivated. And then we can log the outcome as well. And then use the prediction to learn. And this prediction we call a perturbation in the system. It's a second level proposition, second order of reflective proposition. So our reflective propositions are what Piaget calls perturbations. He talks about gaps and other sort of disturbances. So, you know, predictions and other things are perturbations, fall into the category of perturbations. We can also do attempts. So on the motor side, we have a situation, we find an event which leads us to another situation. So we can form an episode around this. We see another event, we form another episode. Then we also can have a process that creates solutions or behavioral schemes. So this corresponds to behavioral scheme, our solution. It has this context, it has actions, and a few other things for bookkeeping purposes. But behavioral schemes that can lead from situations over events to other situations. We can continue to form these. And then if we have a need in the system, we can actually attempt particular behavioral schemes. We can attempt them, and then these are perturbations, so the reflective processes would look at our attempts and determine whether they succeed in the field. So this gets us, we're almost done. Sorry to be so long, but so PAMP2 is a system, and we were talking earlier about divergent thinking. This is a convergent thinking example. It's an amalgam of different systems, largely influenced by Piaget, but also by Roland Hauser, database semantics, dynamic interlaced hierarchies by Richard Mikowski, behavioral schemas by Gary Drescher, who did the schema system, ontology formation by Tiffany Gerkia, and Pickett and Oates, Mark Pickett's from Oates, temporal activation, microperiods, and so forth. So I'll just go through these quickly. PAMP2 uses database semantics. So essentially the system is a database of these neural propositions. And database semantics views language communication as occurring between agents having sensors and effectors, a database, and speaker and hearer modes of communication. So we move the database content from the speaker to the hearer. Dynamic interlace hierarchies. This is the core of the work. Richard Mikowski, he discovered that if you have different hierarchies, shallow concept hierarchies, and you interconnect them, then when you move members of the hierarchy, or you move pointers in the hierarchy, you can get very different kinds of analogical, inductive, and deductive inference. And he determined that you can do generalization, specialization, by just moving things up and down in a hierarchy. You can do abstraction and concretion by adding or removing information, similization, dissimilation. You can do all these different things in deductive, analogical, and inductive ways. So all of these different kinds of inference can be done, performed. And in our system, what he called a trace, I just simply call an entity as a scheme, an entity scheme. Behavioral schemas, Gary Dresser made the schema system. He developed the concept of reification and detecting the causes of failed behaviors through impediment description or failure prediction. And yeah, his system was pretty groundbreaking. And Vipin and Durkee has explored synthesizing ontology from sensory data sets, and Pickett and Oates have built algorithms such as the cruncher and the cruncher, which can construct ontologies from data. And then Doug Leonard talked about microtheories in psych. And we have something similar to a microtheory. It's called a viewpoint. It's just a collection of schemes with activation and belief. And then I looked at a bunch of systems, and I found that there are many patterns in a lot of the cognitive systems that exist. Observation, coordination, reminding, reaction, deliberation, motivation, simulation, regulation, compensation. These are different patterns that exist and which I've included in the PAMP2 system. And this is the system itself. So the body is a device, and it has a perceiver component which receives data sets, sensory data sets, and translates them into percept propositions, which are stored in the memory. And then from memory, so all the blue areas are memory. All the yellow areas are observation. The pink areas are coordination, and the green areas are reflection. We have regulators, compensators, and different kinds of coordinators. In fact, a lot of different highly specialized kinds of coordinators. We have propagators for belief. We have inductors that generate groups of schemes, associators that generate individual schemes, reasoning, inference processes, correlation, consolidation, different kinds of solvers, activators, regulators, compensators. But they're all specialized, they all do one thing. Each one is single purpose. And then finally, the memory of the system. Right now, it's just a relational database, but we have monad schemes in the terms, so the whole neural proposition structure is here. Activation is associated with a viewpoint, which is a context or a situation. We have beliefs. We have data sets that we ingest. Different kinds of relations that are defined, and so forth. And so basically, neural proposition is an amalgam of many different systems. And then lastly, so once you have a mind, where are you going to put it? And how are you going to connect it to the world? So essentially, we would have the PAMP2 instance here, And we have maybe a website of users that log in and register their devices, whether mobile, tablet, laptop, or fine. Maybe this is a Now computer or something, Now robot. And the devices themselves, once registered, would log into a device service, a device login service, and then a mind would be provisioned for them, and then the mind would be connected to the device. You can have different kinds of minds. You can have a single mind with a private database that controls a single device, or that controls multiple devices. You can have multiple minds with shared database that control a single device. In this case, this would be dissociative identity disorder, or many devices, in which case we'd have a hive. And, you know, from a research perspective, we'd be interested in I'm interested in development, so I'd prefer to create systems that are individual or unity, so that way we can measure development. If you wanted to measure evolution, we'd probably go with a hive mind system. And then finally, so we have a mind server, we have the instance, which is here, and then the memory, which is being constructed from model reality. And so it all goes back to Jean Piaget, who said, the central idea is that knowledge proceeds not from the experience of objects or innate programming, but from successive constructions, the result of constant development of research.